Imagine a hairline crack forming in the wing of an aircraft, undetected during routine inspection. This microfracture propagates under stress, eventually compromising structural integrity during flight. Traditional engineering demands constant vigilance and costly replacements for components reaching their fatigue limits. The financial and safety implications of such failures are immense, leading to substantial downtime and, in critical scenarios, catastrophic loss. For centuries, materials science has focused on designing stronger, more resilient substances. Yet, the fundamental challenge remained. Once damaged, a material's inherent properties degrade, necessitating repair or complete substitution. This cycle of damage and replacement underpins much of our industrial infrastructure, creating a perpetual demand for resources and maintenance. However, a new paradigm has begun to emerge: materials that can mend themselves. This concept, once relegated to science fiction, is now a tangible reality, pushing the boundaries of what we understand about material longevity and resilience. The idea is not to prevent damage entirely, but to actively respond to it, restoring function and extending lifespan. Early breakthroughs leveraged encapsulated healing agents. Microscopic capsules containing a monomer are embedded within a polymer matrix. When a crack forms, it ruptures these capsules, releasing the monomer, which then polymerizes upon contact with an embedded catalyst, effectively patching the damage. This method, while ingenious, introduced a foreign substance into the original material. A more advanced approach involves intrinsic self-healing, where the material itself contains dynamic bonds that can reform. For instance, some polymers are engineered with reversible covalent bonds or hydrogen bonds that, when subjected to specific stimuli like heat or pressure, can relink across a fracture interface. This allows for repeated healing cycles within the original material structure. Consider flexible electronics, where a minor tear can render a device useless. Contemporary self-healing hydrogels and elastomers are demonstrating the capacity to repair cuts and punctures at room temperature within minutes. Prototypes of stretchable circuits and sensors have shown remarkable recovery after being severed, restoring electrical conductivity and mechanical integrity, offering a glimpse into devices that resist common forms of wear and tear. Yet, the practical application of these marvels faces significant hurdles. While impressive at the microscale or for surface-level damage, scaling these healing mechanisms to larger structural components with complex load-bearing requirements introduces substantial challenges. A small scratch on a smartphone screen is one thing, a deep fatigue crack in a bridge girder is another. The efficiency of self-healing is often inversely proportional to the extent of the damage. A material might effectively close a sub-millimeter crack, but struggle to bridge a gap of several millimeters, or repair damage that involves significant material loss. Furthermore, repeated healing cycles frequently lead to a gradual reduction in the material's original properties, preventing indefinite repair. Material design complexity also presents a substantial obstacle. Integrating self-healing capabilities often necessitates a compromise in other critical properties such as strength, stiffness, or thermal stability. Achieving a balance where the material is robust enough for its intended application yet flexible enough to self-heal without extensive intervention requires sophisticated engineering and often novel chemistries. Environmental factors critically influence healing performance. Many current self-healing mechanisms are sensitive to ambient conditions, requiring specific temperatures, humidity levels, or even UV light exposure to initiate and complete the repair process. This limits their applicability in uncontrolled environments, such as outdoor structures or components operating under extreme conditions. The economic viability remains a significant barrier to widespread adoption. The specialized materials, complex manufacturing processes, and precise engineering required for effective self-healing often translate into significantly higher production costs compared to conventional materials. Unless the cost-benefit analysis demonstrates clear long-term savings in maintenance and replacement, the incentive for industries to transition remains low. Furthermore, there is the risk of unforeseen failures. Incomplete healing, where a crack appears to be mended but retains a weakened internal structure, could lead to more insidious and dangerous failures than a clear, detectable break. Relying on an invisible repair mechanism requires rigorous validation and robust diagnostic tools to ensure the integrity of the healed section, adding another layer of complexity. Despite these limitations, research continues to advance, exploring new avenues such as bio-inspired healing, where vascular networks deliver healing agents to the damaged site, mimicking biological systems. Another direction involves using external stimuli like electrical currents or magnetic fields to trigger and control the healing process, making it more adaptable to real-world scenarios. Self-healing materials are not a universal panacea for material degradation. They represent a sophisticated tool in the engineer's arsenal, best applied where their unique capabilities can address specific failure modes and extend the service life of critical components, provided the limitations in damage scale, healing efficiency, and environmental sensitivity are thoroughly understood and accounted for. The journey from laboratory concept to industrial application is protracted, demanding continuous refinement and a pragmatic assessment of both their remarkable potential and their inherent constraints.